So you have learned that the derivative of a function at a point is the slope of the tangent line to the curve at that point. It's also called the gradient of the tangent line. So what if we had a function and we calculated a whole bunch of derivatives at different points on that curve? And then what if we looked at all the x values and corresponding derivative values? Well, it turns out that that set of ordered pairs itself makes another function. And it's the general derivative function of your curve. So if we take the derivatives at every point of a function f, that itself will be a function, and it's called the general derivative function of f. Might sound a little confusing, so let's look at an example. Using first principles, find the general derivative of f of x equals 3x squared minus 1. So what we did before is we had a certain value, a certain x value, where we were finding the derivative at. Well, here we don't have a specific x value. So we're going to do the limit as h approaches 0 of f, instead of f of a plus h, where a is a specific number, we're just going to call it x plus h minus f of x all over h. So it's almost exactly what we did before, except we used a instead of x. In terms of thinking about it on a graph, if I have a function f, looks something like that, and instead of finding it at one specific point, I can find it at any point. We'll just say x, and then somewhere that's kind of close to that would be x plus h. And so then the output here would be f of x, and the output here would be f of x plus h. And so then to find the slope between these 2 points would be the difference of the y's over the difference of the x's. And then if we simplify, those x's cancel out. And then if we take the limit as h gets closer and closer to 0, which would bring that second point closer and closer and closer to this first point, and instead of the slope of the secant, we would be getting the slope of the tangent. All right, so we're generalizing here, and we're not using a specific x value. We're leaving it as x. So therefore, our derivative is going to equal f of x plus h. So I'm going to look at my f of x function, and I'm going to plug in x plus h wherever I see x. And I'm going to put that in brackets so it's easier to identify. And then minus f of x, which is 3x squared minus 1. And so you're going to notice before we were plugging in a number instead of where I have x here. And so our answer was going to be a number eventually when we took the limit. And that number represented the slope of the tangent line at that specific point. Here, our answer is going to have x in it, most likely. And so our answer is going to be a function. It's called the general derivative function. So now it's just a matter of doing some algebraic simplification. So let's go ahead and square. If I square x plus h and then multiply everything by 3, I'm going to get a 3x squared plus, and then I'll have a 2xh times 3 is 6xh, and then 3h squared, and don't forget the minus 1, and then minus 3x squared minus 1. And all of that is over h. I cannot evaluate the limit yet because if I plugged in 0 for h, I'd be dividing by 0. And now we notice these 3x squareds will cancel, and then negative 1 minus a negative 1 is negative 1 plus 1. Those cancel. And then, like we've done so many times before, we could factor an h out of the 2 terms that are left in the numerator, and I'll have a 6x plus 3h to the first over h. And then h over h reduces down to 1. And now I can take the limit, and this is where sometimes students get a little confused, but remember, we're looking at the limit as h approaches 0. So in my expression, here's h. So if I plug in 0, I get 3 times 0 is 0. But over here, this is a different variable, it's x. x is not affected by h going to 0. X just stays as x. So any other variable besides h is unaffected. So what we're going to wind up getting here is 6x plus 0. So it's the limit as h goes to 0 of 6x plus 3h. And as h goes to 0, this term goes to 0, and we're left with 6x. And so that's our general derivative. And the notation that we use for the general derivative is f prime. Do this in a different color. So f and a little tick mark, f prime of x equals 6x. And so that's the general derivative function. So now if I say, well, what's f prime of 4? Well, it's going to equal 24. That means for my function, at 4, the slope of the tangent line is 24. So now I wouldn't have to calculate the specific derivative at a whole bunch of points if I needed to. I could just use my general derivative and evaluate it at each of those x values. Okay, let's try one more example. This time I'm going to go a little more quickly. So let's find the general derivative of this. Limit as h approaches 0. F of x plus h will be 1 over x plus h, minus f of x, which is 1 over x, and then all over h. I realize it's a g function, but it's the same idea. So now in order to simplify this, I'm going to multiply the first fraction by x over x, and the second fraction by x plus h over x plus h. That'll give me a common denominator, and then I can combine those two fractions. So I get the limit as h approaches 0 of x minus x plus h, I'll use parentheses so I don't forget to distribute that negative sign, over the common denominator, which is x times a quantity x plus h. And then all of that is over h. But we know dividing by h is the same as multiplying by 1 over h. So there goes my complex fraction. So now if I simplify what I have the limit as h approaches 0. In the numerator, I'm just going to be left with a negative h. And in the denominator, I have x times a quantity x plus h times h. And then negative h over h reduces down to negative 1 over 1. And so now I have the limit as h approaches 0 of negative 1 over x times the quantity x plus h. And as I said in the previous example, x is unaffected by h going to 0. So now I can plug in 0 for h, and I'm going to get negative 1 over x squared. And so what we have just calculated is g prime of x, or the general derivative of g. So g prime of x is equal to negative 1 over x squared. And now I could find the derivative of g of x, or the slope of the tangent line to g of x at any particular x value, simply by plugging in that to my derivative function. All right, so the assignment is worksheet 3.